Hello, everybody. Good evening to all of you. Today's lecture on linear induction motor on performance analysis of linear induction motor. Previously, we completed that thrust equation. Next, thrust equation we completed previously, and next we're going to discuss about the performance analysis or performance equation of the linear induction motor. How we are getting the linear induction motor performance analysis and also equivalent circuit, and also furtherly we are getting some of the losses also, and how the linear induction motor can be controlled. These are the topics we are going to discuss now. And this is the thrust equation. We previously discussed that this is thrust equation or thrust force equation. 1.11 eta LW KW turns per phase B average AC cos pi. And next one, losses in a linear induction motor. Those losses are nothing but transverse edge effect and also the end effect. These two effects are the main losses in linear induction motor. And furtherly, there is no rotating losses. There is no rotating. Why? Because it is a linear induction motor, and which the application of the machine can be run using linear motion. So that's why we are not having any rotational losses. So we are going to discuss about the losses related towards the linear induction motors or transverse edge effect and also the end effect. And next one is the analysis, performance analysis of the linear induction motor. And this is the actually for the analysis of the linear induction motor, the actual slots, the actual slots and the structure of the primary are replaced by a smooth surface. Here, if you consider, actually, this is the secondary core. Secondary core, this is secondary core, and this is the in the below diagram which is showing here is the secondary core, and also that this is nothing but the slots or secondary bars. Even it is a winding, or even if it is not a winding, some of the applications of the linear induction motor, we are using the winding, and some of the applications we are not using any winding. Secondary bars are there within the slots, and these bars are placed on the secondary side. And next one, and this is the primary slots and the primary core, and primary winding has been placed within the slots. Here, in this analysis, the actual slots and the structure of the primary are replaced by a smooth surface, and a current carrying conductors are assumed to be infinitely the thin current elements. Nothing but we are making a smooth surface, nothing but there is no external part of the primary coils which are coming outside. Not like that. There is a smooth surface in between these two. So we are having that smooth surface by using the current carrying conductors also. And these thin current elements are called current sheets. These current elements are called current sheets, we called as, and current sheets is assumed to have linear current density. Here, the thin current elements are called the current sheets, and the current sheets have to be having the producing or a linear current density, which is coming from the flux. That is, current sheet have linear current density. And next one, if you consider a sinusoidal, a sinusoidal distribution of winding, this is not possible in linear induction motor. Normally, sinusoidal distribution, actually in a rotating magnetic field, if you observe, in a normal conventional induction motors, not a linear induction motors, in a normal conventional induction motors, if you come across the rotating field, how the field can be supplied from the supply, main supply. That is using that a sinusoidal flux distribution is moving within the air gap. That is the flux distribution. rotating magnetic field is revolving on the air gap of a normal conventional induction motors. But it is not possible a sinusoidal distribution in linear type induction motor. Nothing but these type induction motors are not possible of getting sinusoidal distribution of the winding. So this results in production of mmf with several harmonics. The thing but this is one of the disadvantages also to produce production of the harmonics. So if there is a sinusoidal distribution, there is some harmonics, but not that much more compared towards the linear induction motors. So this results in production of mmf with several harmonics, and generally the fundamental component is considered for the analysis. Here this is nothing but the some of the variables or constants we considered here. Here a1 is nothing but let a1 is equal to peak current density, first one, peak current density of the sign distributed current sheets of the primary. Peak current distribution, nothing but here if it is considered primary and it is the secondary side. So a1 is the peak current density of sign distributed current sheet of the primary, ampere per meter square, first one. And next one, this is nothing but the a2, peak current density of peak current density of sign distributed current sheet of secondary, ampere per meter square again. And F1 is the peak mmf produced of a current primary current per pole. And F2 is nothing but the peak mmf produced by the secondary current per pole. LZ is the length of the air gap, and L suffix T is nothing but the free displacement. Free displacement, and Fe is nothing but thrust per wavelength, rho resistivity, and sigma conductivity, mu naught permeability of free space, and d is the thickness of the plate. Nothing but these are considered in between these two, primary and the secondary. So, and finally, how the equation can be getting from the performance analysis, we can observe here. Consider the primary and the secondary of the linear induction motors in the figure of above figure. The primary secondary slot currents are assumed to be of sign distributed current sheets. We are assuming, make an assumption of sign distributed current sheets, and the current sheets produce mmf per pole of peak values, and this is nothing but the mmf produced by the primary, and this is the mmf produced by the secondary. That is f1 is equal to tau by pi a1, and f2 is equal to tau by pi a2 value. These are the basic expressions which we are derived in the previous also. So we are getting that mmf per pole of peak values from primary side and also the secondary side. And next one, how the thrust per wavelength is to be getting. Thrust per wavelength. This is equal to thrust per wavelength. And next one, if you come across the if you come across the these are nothing but we are integrating this wavelength values of thrust per wavelength. And next one, we are converting into uh, power input towards the secondary. How the power input towards the secondary, we can getting that P2 is equal to tau k s b1 square. Here, what is these expressions means here? These expressions are derived not in form of the rotating nature, but in form of linear. So we are getting these waveform, these expressions. P2 value, secondary power input towards the secondary means P2 is nothing but a air gap power or a rotor input power or air gap power. We'll call it as P2 is equal to tau k as B1 square. And the mechanical power developed is a common value. PM is equal to P2 of 1 minus S slip times. And this is the copper loss, P2S value, rotor input into S value. Here, what we observed from the rotating induction motor, what we observed in the rotating induction motor, same we considered in the linear induction motor as the ratio, same as that of the ratio. So if we consider P2 is the rotor input, mechanical power developed, and P suffix C is nothing but the copper losses. So we consider as 1 is to 1 minus S is to S. These values are getting by dividing with respect to the again rotor input value P2. So P2 by P2 and PM by P2. Then we are getting 1 minus S P suffix C by P2 value. P2S by P2. So we are getting the S value. P2 P2 cancel. Rotor input. And this is the ratio. Nothing but finally what we are getting for a normal conventional induction motors, what we are getting as the same sense of linear induction motor has the ratio is a getting, but it is in a linear motion. The induction motor in a linear motion. These expressions are how we are getting means I will explain these expressions of P2 rotor input power. I will explain that generally we considered induced EMF. How the EMF induced in the secondary side of the rotor of the linear induction motor. How the EMF induced in the secondary side of linear induction motor and how we considered. And with respect to this, how much amount of current can be produced? What is the expression? I will tell that that is the induced EMF of the secondary side actually E is equal to B1x L times SVS. What is the SVS means? Here we considered as B1x is nothing but the air gap flux density at X point. What is X point also I will explain here. One minute, just here. Yeah. Uh, Initially, just we considered that here just we considered how the primary and how the secondary can be considered. Nothing but drawn with respect to that. I will explain with some drawings. Just wait. Here, just we are considering the primary and secondary. We are considering the primary and secondary. How the primary and secondary in terms of linear motion, linear induction motors can be expressed. Uh, with a single line diagram, or even we consider in with x-axis and y-axis, or we consider as a direct axis and quadrature axis also. How the direct axis and quadrature axis to be, we can explain. Uh, and this is the expressions, how we are getting the induced EMF, and how we are getting the mechanical power developed, we considered. This is the d axis, nothing but direct axis, and I will show with you another one, quadrature axis. This is the direct axis, and also the we considering the quadrature axis also. Why? Because in a machine completely we considered as a direct axis and also the quadrature axis both. So this is the, this purple color I am showing here is a quadrature axis. This is the direct axis, and this is the quadrature axis. Here it is the quadrature axis. Direct axis, quadrature axis. You know the difference between these direct axis and also the quadrature axis. Direct axis is directly with respect to the pole pairs, okay, of a primary. If you consider second primary, then what about the quadrature axis? In between the poles, in between any north and south poles, they have a axis, that is the quadrature axis. Air gap is to be more on, normally air gap is more with respect to quadrature axis, air gap is less for direct axis. If you consider a, we, that is a sinusoidal distribution. If you consider as a sinusoidal distribution, nothing but we are making an assumption. This is an assumption. Here we are considering the sinusoidal distribution. Here it is the sinusoidal distribution of the, this is the sinusoidal distribution with respect to primary, and this is the primary. I am calling as a, this is the primary. Actually, in the diagram, we you observed that primary and also the secondary. Above that is a primary, below the primary, and also above that is a secondary side. Here again we are considering here a sinusoidal distribution. Why? Because we are considering both for primary and also the secondary. How the peak flux density can be, peak flux with respect to sign distribution, how the waveforms should be. Uh, Here we are considering here on the secondary side like this. Why? Because secondary is also producing some mmf with respect to primary, with respect to primary. So there is a difference, there is a difference. and again this is the quadrature axis. I am drawing with the same color of orange. This is the, once it is the direct axis, again it is a quadrature, again it should be a direct axis, like that. Not with the same value of a direct and quadrature, it should be changing. It is a direct axis and it is a quadrature axis. So with respect to these, here if you consider, this is the a1 value, that is a1 value is nothing but uh, peak current density of a sign distributed current sheet. Peak current density. A2 is nothing but a peak current density of a secondary side. Here we are considering it as a A1 value. Here it is a A1. It's a A1. Here it is a A2 value. How the A2 value should be? We consider only for positive side, positive of response. So this is the A2 value. If you consider, this is the A2. This is the A2. And next one, linear motion. Linear motion means this is in x direction. If you consider, this is in x direction. Linear motion, this is the in the form of a x direction. And here if you consider how the current density to be, then we, if you consider what, if you these sinus distributed waveform can be spread out into, taken out from this diagram. Suppose this is the primary and this is for secondary. This is for secondary. Here if you consider, we are getting some sign distributed waveform here, sign distributed current, and here we are getting some sign distributed current here. So by comparing these two, what we are getting, the sign distributed waveform should be changing. The sign distributed waveforms, if you observe, this is the sign distributed waveform for A1. This is the sign distributed waveform for A1, and this is the for a negative half cycle, if you consider negative half cycle. So this is the for primary side, and the next one we are getting the secondary side like this. How the secondary should be? The secondary should be, we are considering the A2 amplitude means like this. Here it should be, this point is to be starting from here. Suppose we consider as a, this point is to be starting from, and this is the, nothing but here the peak current density of each current sheet should be changing. This is for primary side and this is for the secondary. So if you consider the sign distribution and how about the peak current density, the peak current density of the primary and also peak current density of the secondary sheets are changing, that is the difference. So what about the EMF induced, and also some of the produced current is also different with respect to the linear induction motor. And this is the diagram. And next one, goodness factor. What is meant by goodness factor? A goodness factor is a criteria. Goodness factor is a criteria for a non-conventional machines. It expresses the capability of a machines to convert air gap power between the secondary and primary in electrical form and mechanical form at a speed related to primary field speed. This is the goodness factor, and this can be derived. This is the having also expression also. A goodness factor G is equals to mu naught permeability of free space by rho into D by LZ into V square by 2 pi f. Vs square by 2 pi f, and this is nothing but the goodness factor. And the nothing but the goodness factor which predicts the performance of the linear induction motor. That is nothing but the goodness factor. Actually this is uh, mostly given for the double sided linear induction motor. Double sided means we are using double primary with a single secondary, so that is used for double sided linear induction motors. and this goodness factor tells about how the performance of the lean induction motor should be. And uh, and also we're having another, this is related towards the equivalent circuit of the linear induction motor. Here, a convenient way, this is the equivalent circuit of a linear induction motor. A convenient way of representing the linear induction motor is nothing but an equivalent circuit. How the nothing but even if we go for use any transformer, how the transformer can be represented, how the transformer can be represented. That is a convenient way of representing the linear induction motor is nothing but equivalent circuit. The equivalent circuit contains inductances, resistances of some variables that are functions of speed also. Let us consider a very simple case of idealized machine with a perfect machine. Simple, I will explain some example. A simple case study, that is with a perfect magnetic circuit and no stator resistance. A resistance connected across the supply represents an idealized induction motor at a standstill condition. We know about the standstill and also the running conditions also of an induction motor. A standstill condition, it represents the standstill condition, and if the motor is allowed to start and move, it produces some power. And next one, the simple resistance cannot represent a machine when it moves. The resistance should represent the power input. The resistance should represent the power input to the secondary given by R2 by S. R2 means a rotor resistance by S value, that is considered from secondary side, which depends on the slip. Yes, at a standstill condition, the slip is to be different, and also at running condition, the slip is to be different. With respect to these parameters, we are considering here, with respect to changing of the slip values, here the induction motor performance is also changing. I think, but why? Because the inductive reactance is to be occurring while using any while running condition, and also while at starting condition, the inductance values to be very low, like that. With respect to inductive reactance values, inductance and also the inductive reactance values, the slip may change the values. Next one, these resistances may be divided into two secondary copper losses. Two categories. That is, first one is a secondary copper loss, and next one other one is the output of the motor. Secondary copper loss and also the motor output of the motor. Here, the motor output is represented by a fictitious resistance. Fictitious resistance is nothing but equal to the fictitious resistance, which is equals to R2 times of 1 minus S by S. This is the equation. To this circuit, the secondary leakage reactance X2 is added. Now, let us assume that the magnetic circuit has a finite reluctance. We will observe in the diagram. These are the diagrams here. If you consider, and this is the equivalent circuit of linear induction motor, and here we consider the equivalent circuit of a linear induction motor. If you consider here, this is the secondary part. Here we consider the R2 times of 1 minus S by S. That is, this is nothing but the fictitious resistance. Fictitious resistance here, this is nothing but represents that motor output or output power of the motor. Here, the secondary leakage reactance X2 value, the secondary leakage reactance X2 is added here, which we are showing in the diagram. R2, we know that R2 times of 1 minus S by S value, and next one X2 value, X2. And here X2 is added, and just we are now assuming that magnetic circuit has a finite reluctance and hence some MMF and current is required to set up the flux. Then these resistance, and furtherly we can express with a magnetic reactance X suffix M. And power loss in the iron part of the motor is represented by resistance Ri. This is nothing but core loss. Power loss related towards the iron part of the motor means it is considered as a iron part, means iron losses or the core losses, which are considered as a constant losses for any motors. Here, next one represented with Ri. Next one, it should be considered a secondary. Finally, the primary leakage reactance, the leakage reactance, final in the final diagram here, x1 we considered, and the resistance R1 are included to get the equivalent circuit. These are the parameters which we consider to develop any equivalent circuit of a motor. But now here we considered R2, that secondary resistance at a standstill condition, and also the output of the output power of the motor. And next one, leakage reactance X2 value in the B diagram. Next, X2 R2, in next one R2 times 1 minus base is the output power of the motor, and the I2 is the secondary current. And next one, from the secondary towards the primary we considered here in the C diagram C, you represent that this is the secondary part, X2 dash R2 dash, nothing but while all the primary values we refer towards the secondary side, all the primary side values are referred towards the primary side, that is x2 dash r2 dash and also r2 dash times of 1 minus s by s. And next one, representation of the diagram D, here the total equivalent circuit of, while we considered that iron losses also, we are considering here. So that is ri, iron part of the resistance, and next one xm is the magnetic reactance, magnetic leakage reactance, and x1 is the total reactance will be considered, r1 x1 r2 dash x2 dash and next one r2 dash times of 1 minus s by s value. This is the complete equivalent circuit of a linear induction motor, the diagram D. And next one, how the characteristics of a typical linear induction motor should be. Here if you consider how the characteristics of any linear induction motor should be. Here, the characteristics are drawn for the slip x on x-axis and also y on y-axis, efficiency, power factor, and also the thrust force. We considered.
దానికి ఒక మెసేజ్ వస్తుంది ఈ అబ్బాయి చేసిన దానికి అమ్మో
Next one, on x-axis slip has been considered, and on y-axis efficiency, power factor, and thrust. Then how the efficiency? Here if you consider, initially there is a slip value initially. Here if you consider, the efficiency value up to the 0 point slip, having a linear motion, after that should be having a linear, but it should be moving towards the zero value, nothing but while we are considering on the y-axis, so the efficiency should be like this. And about the power factor, it should be dropping, the power factor value should be coming towards zero nearly. Means here initially there is no load, suppose initially there is no load, and next one after that, whenever the load value has been increases, even if we consider from this side also this side. And how about the thrust value? The thrust force should be, initially it should be zero and it should be rising, or increasing towards the maximum value, after that should be dropping with respect to 1, slip 1 value. And frequency versus thrust curve, how the frequency versus thrust curve should be means here like this. Actually this is the design frequency, given that it is the design frequency value. Okay, and next one, if it is furtherly increases means the frequency value is increases, but what about the thrust force is to be decreasing, nothing but whenever the frequency value is increases furtherly, suppose it should be 50 hertz, suppose we consider 50 hertz or 60 hertz, even if it is increased more than the value means, so what should be happen means the thrust force should be drops towards the zero value. like that. The next one, how about the voltage and air gap length value, and also with respect to thrust force? Here, whenever the voltage values increases means there is increasing of the thrust force. Why? Because directly proportional to the Vs square, torque directly proportional to the torque or thrust force, whatever it may be, which are directly proportional to the square times of the supply voltage. So it should be increasing drastically. It should be increasing drastically. So that is the change. And with respect to air gap length, nothing but whenever the primary and the secondary values, air gap length value has been increased, suppose primary and secondary air gap length has furtherly increases. So what should be happen? If suppose air gap length is should be suppose this much mm, so there is no much difference, and the thrust force should be this much value. Suppose if it is having the air gap length on this point here, the thrust force should be this much. But what about the whenever the furtherly air gap length value has been increases, suppose air gap length has been increases, then thrust force has been decreases drastically. It is decreases furtherly with respect to the increase in the air gap length. And next one, performance of the linear induction motor depends on the air gap, pole pitch, number of poles, and thickness of the secondary, resistivity of the secondary, and tooth width of the primary. These are the values, nothing but how the performance of the linear induction motor, on what factors it should be depend. That majorly depend upon the air gap value first. Yes, we will consider that one in the graph. Whenever the air gap value has been increased, the thrust force has been decreases. And voltage value, whenever the voltage value decreases means it should be thrust force has a low value. Whenever increasing means there is a thrust value increased value, but having a some limit also. With respect to the voltage is having also some limit. At one point there is a limit, no, not further increases voltage values. Even whenever the voltage value increases, there is no possibility of increasing thrust also. There is a burning of a winding on the primary side with respect to the supply given towards the distributed winding. Here next one, the performance of the linear induction motor depends on air gap, pole pitch value, and next one, number of poles, how many number of poles are placed, the next one, thickness of the secondary side, and next one, resistivity of the secondary and tooth width of the primary. These all we considered. Next one, a large air gap length increases the magnetizing current, and exit losses are decreases. Sorry, end exit losses are more and decreases the goodness factor. What we decreases what the factor, what parameters can be decreases means goodness factor, thrust, and efficiency values. Yes, we observed that on the graph previously, previous slide. On while increasing the air gap length, this is the air gap length, the thrust force is decreasing. And also what are the decreased parameters means efficiency decreases and goodness factor also. Next one, higher pole pitch increases the goodness factor and reduces the number of poles required. Here this is the important point we considered for the performance of the linear induction motor. That is, pole pitch is whenever increased means goodness factor has been increases, and at the same time reduces the number of poles. We don't require much number of more number of poles. North pole, south poles we are having, but no number of poles are to be reduces. And next one, we are having some design aspects of linear induction motor. These are we considered on thrust force equation and also some of the performance analysis of a linear induction motor, but we considered mostly on thrust force equation. That is the choice of a specific magnetic loading, choice of specific electrical loading. How, what are the values we considered while we designing, what are the aspects we considered while designing any linear induction motor means on choice of specific magnetic loading we are considering power factor, iron loss, overload capacity. And next one, choice of specific electric loading, permissible temperature rise on the winding itself, size of the machine, current density, voltage, overload capacity. On the specific magnetic loading and also specific electric loading, these two important parameters we considered while we designing any linear induction motor. So these are the important. aspects. Next one, design of the primary. Suppose we consider shape of the slots. Semi-enclosed slots are generally used for linear induction motors operating below 600 volts, and these type of slots give good performance and higher efficiency in the use of material. Use of semi-closed slots reduces the tooth pulsation and leads to a quieter operation. Next one, choice of number of slots, tooth pulsation losses, leakage reactance, mechanical difficulties, nothing but we choosing number of slots. Number of slots also may play an important role where tooth pulsation losses can be reduced as leakage reactance, mechanical difficulties, magnetizing current and iron losses also reduces. And if you go across the primary winding means here, and these are the points, and that is the length of air gap, cooling, magnetic pull, pulsation loss, and noise, power factor, and overload capacity. And if you go for the primary winding means the coils are wound on mold and then placed into the slots. These are normal aspects, design aspects for any induction motor. But we considered for linear induction motor means somewhat different with respect to the conventional induction motor. That is the major one. In the next class, we will discuss about the. I hope all of you understand about this performance analysis and also um, these characteristics, various characteristics of the linear induction motor and design aspects. Within the next class, coming next class, we will going to discuss about the different types, classifications of linear induction motor furtherly. And next one, problems. Some of the problems we are going to discuss and how the linear induction motor can be controlled. And these are the topics we considered on the coming sessions. Thank you.